So last class we discussed, as long as stress is proportional to strain, okay, the ratio of stress to strain is called modulus of elasticity, and the ratio of longitudinal stress to longitudinal strain is what you call Young's modulus. Okay, and mathematically we write it this way: longitudinal stress is perpendicular force per unit area, unit cross-sectional area. Longitudinal strain is change in length divided by the natural length. This becomes Young's modulus. And rearranging this equation, you can say change in length is F perpendicular by A into L naught divided by Y. But I told you, if you want to apply this formula to calculate elongation under the action of a stress, okay, you can apply this only when the stress, longitudinal stress, is uniform over the entire length. Obviously, how much strain you get depends on the stress, right? Now, if stress is same everywhere, you can directly use this formula. Otherwise, you'll have to split it into small parts. Okay, that is what we will work on today. Last class, we discussed cases where the stress is uniform. Okay? For example, yeah, this case where the cylinder is being pulled by the same amount of force in opposite directions. This creates uniform stress. We found out elongation. Here, there were two parts into which we divided this object. On the narrower part, there was uniform stress, one amount of uniform stress. On the wider part, there was a different amount of uniform stress. So we split it into two separate parts. We found out elongation in the narrow part, okay? And we found out elongation in the wider part. And you add the elongations, you get the total elongation, okay? Delta L1, delta L2, you add them, you get the total elongation. So if the stress varies from point to point or place to place, you say, then you will have to find out elongations in small parts where the stress is uniform. Okay, that's the idea. That is what we'll work on today. So consider this situation. Just a moment. Let me copy the cylinder. Okay. Assume this is a cylinder whose total mass is m, total length is L, area of cross section is A. Okay, it has a uniform area of cross section. It is made of the same material throughout. If the material is same everywhere, that means the Young's modulus is same everywhere. And let's say it is being pulled to the right by applying a force F. We are applying force only on one side. Okay. First thing I want you all to find out is how much stress is produced at a random cross section which is at a distance x from the free end of the wire, the end where the force is not applied. From there, at a distance x, I want you to find out the longitudinal stress. Now, how do you do that? See, the wire is being pulled at one end. When you pull something, it has a tendency of getting stretched. Okay. So what you are generating in this is a tensile stress. There will be tension developed. Now, in laws of motion, if you remember, we had solved problems like this. Multiple blocks connected by strings, and you apply a force on one side. We used to find out tension here, tension here. Fine. Situation is something similar in this case. So there will be tension generated in this cylinder. So at this random distance x, you need to find out how much is the tension. Now, how do we do that? If you want to find out tension anywhere in a particular system, see, tension is a force. If you want to derive an expression for force acting anywhere, you need to first visualize a part of the system for which that force becomes an external force. Now, for the entire wire, if you see, tension is an internal force. But if you consider only this part of the wire, okay, if you consider only the left part of the wire or only the right part also, then tension becomes on that part, tension becomes an external force, and you will be able to write Newton's second law F net equal to ma involving tension and derive an expression for it. Okay, so Try this, both of you. Derive tension first. Tension divided by area will give us stress. Once you know the stress at different points, you can find out, I mean, you can take the next steps and find out the elongation in the wire. Okay, we'll do that. Derive an expression for tension at that distance x. Do this, both of you. Fine. See, the aim is to calculate tension at one particular cross section. Now, we have identified a part of the system for which tension is an external force. Without doing that, you can't write an expression, or you can't write Newton's second law with tension in it. Okay. So we have identified a part of the system for which tension is an external force. Let's say that part's mass is small m. Then on that part, tension is the only net force acting, only force acting. Then you can write tension is equal to small m into a. So if you know the acceleration of that part of the system, you can tell how much is the tension. Now, how to find out acceleration? Now, this is a rigid cylinder, solid cylinder. The entire cylinder will have the same acceleration. So to find out acceleration, you can look at the forces acting on the entire system. And the net force acting on the entire system is capital F. So you can say capital F is equal to capital M multiplied with A. So A is F by M. Now every part of the system moves with the same acceleration. So this part also will have the same acceleration F by capital M. Therefore tension becomes small m into F divided by capital M. But we don't know small m, the mass of that part of the system. How to write mass of a part of a system? We had done this many times. You look at the kind of mass distribution. Now a cylinder is a volumetric mass distribution. So total mass by total volume should be small mass by small volume. Or if you want to distribute mass this way, you can even call it as a linear distribution. We had discussed this in the last class. Okay. Let's go for volume distribution itself. Total mass by total volume of cylinder. Volume is area of cross section into length. Should be equal to small mass divided by small volume. Area of cross section multiplied with the length. The length of the small part that we took is x. That's all. Capital A gets cancelled. So small m becomes capital M x divided by L. Substitute this here. You get tension there as capital Mx by L multiplied with F divided by M. Cancel. Tension becomes Fx by L. Okay, let us understand what this means. Now for the left end of the cylinder, x is 0. Now we got tension as Fx by L. If x is 0, tension is 0. So at this end, the tension is 0. Exactly at midpoint of the wire, x becomes L by 2, wire or cylinder, x becomes L by 2. Now we got tension as Fx by L. So F into L by 2 divided by L. So the tension there becomes F by 2. Similarly, if you see, the tension here becomes equal to F. So this is a clear case of non-uniform tension. Area is same everywhere, but tension is not same everywhere. So T by A, stress will not be same everywhere. So this is a case of non-uniform stress. Fine. Now we have the expression for tension at a distance x from the left end. If you have the expression for tension, then you can write the expression for stress. And if you can write the expression for stress, you can find out the strain, that is the elongation in the wire. So we got tension here as Fx by L. Now see, tension varies based on the distance from the other end of the wire. Okay. So from distance to distance, if it is varying, clearly it's a non-uniform stress. But if you want to find out elongation, the only formula you have for elongation is elongation is equal to F by A into L naught by Y. Now, if F by A, if the stress is same everywhere, you can apply this to the entire wire at once. But now you cannot, stress is non-uniform. So you have to take elements where the stress can be assumed to be uniform. And how do you take such elements? They have to be small elements like this. From one distance x to the next distance, okay, whose length is dx, in which the length is dx. Over that part of the cylinder, you can assume the stress is same. Okay. What is the original length of that part of the cylinder? Dx. In that dx, you have to find out how much is the elongation. So let us apply this formula. The length to which we are applying this formula is dx. The stress on the element to which we are applying this formula, force is Fx by L, area is A. So the stress is Fx by LA. So we got stress, we got original length. With that, we can tell what is the elongation in that one small element. I'll call it dl. Therefore, elongation in that small element becomes Fx dx divided by L A y. And if you want total elongation in the wire, you'll have to integrate the elongation in every element. So you'll need to integrate, see f by LAY, these are constants. You'll need to integrate x dx. And to cover the entire wire, x varies from 0 to length L of the wire, 0 to L. Integral x dx is L square by x square by 2. After substituting limits, it becomes L square by 2. One L gets cancelled. You will get the total elongation in the wire as FL by 2A pi. Okay, let's quickly go through this one more time. You are given a situation where a cylinder is being pulled at one end with a force F, and you are asked to find out the elongation in that cylinder. Elongation means deformation. Deformation is caused by stress. So you first had to derive an expression for stress. So we took a random cross section somewhere, derived an expression for tension there. And from tension divided by area, you will get stress. Now, since the stress is non-uniform, we choose one small length dx over which the stress can be assumed to be uniform. Okay. In that small length dx, we find out how much is the elongation. And then we integrate that small elongation over the entire length to find out the total elongation of the wire. Okay. So hope the idea is clear to you. Let us try this, or let us apply this idea to a situation we kind of already dealt with, this one. In this question, yesterday or last class, you were asked to find out what is the tension at a distance x from the free end. And we saw that tension is non-uniform. Okay, we got the expression for tension also. Just a moment. So yeah, if a wire is suspended like this, fine, we can remove this part. You know tension will get generated, non-uniform tension will get generated. Let's say it's a wire of total mass m, length L, cross-sectional area A, and Young's modulus is Y. Because there will be stress generated in it, it will definitely elongate. Okay. So what I want is you to derive an expression for elongation of the wire under the influence of its own weight. Okay, try this all of you. I'll give you the steps also. First, derive tension as a function of x. Once you do that, divide it by area, you will get stress. Then you will see that the stress is non-uniform. So what you can do is you can assume that for a small length, okay, maybe from here to here, for a small length dx, you can assume the stress to be uniform. So what will you do next? You will write an expression for elongation in that small length. And finally, you will integrate elongation in the small length to get elongation in the complete wire. Okay. Do this quickly, all of you. I'll give you all 3 minutes. See, the tension at a distance x from the free end we had derived yesterday itself. It is mg x by L. Fine. M is the total mass, L is the total length. Fine. Then tension by area simply becomes mgx by AL. Area of cross section is uniform throughout. So you can write mgx by AL. So this becomes the longitudinal stress, where at that distance x from the free end. Now from distance to distance, the stress is going to change. What we want to find out is the total elongation in this wire. We have a formula for elongation. based on Young's modulus y is equal to stress by strain, we have elongation is equal to stress into natural length divided by the Young's modulus. But as I said, this is applicable only if the stress is uniform. Fine. Here, from distance to distance, the stress varies. So for the entire wire, the stress is not uniform. So what you can do is you can take an element of the wire like this, the orange element that I have highlighted. If the length of the element is very small, like dx, you can assume there is uniform stress on that element. Okay. And if there is uniform stress, we can use this formula to find out elongation. Now, the length of the element you have taken is very small. Therefore, the elongation in that element also will be very small. Okay. So, elongation in one element will be stress F by A. Stress is mgx by AL. Substitute that. Multiplied with natural length of the element divided by the Young's modulus. That's the elongation in one element of the wire. And you integrate this, you get the total elongation in the wire. So mg by A, okay, L is total length. Total length I'll denote by capital L. Ly integral x dx. And to cover the entire wire, x should vary from 0 to capital L. We want elongation in the complete wire. Now see, they may ask you what is the elongation only in the lower half of the wire, only in the upper half of the wire, or from certain length to certain length also they may ask. Accordingly, you have to adjust the limits. We want total elongation in the wire. So limits will be from 0 to L. Integral x dx is x square by 2. Substitute limits. This becomes L square by 2. 1 L gets cancelled. So the total elongation in a wire under the influence of its own weight becomes mgl by 2ay. Okay. The question we solved before this also is very similar. In the previous question, you were given a cylinder where a force F is applied only at one end. If you apply force only at one end, net force is not zero. Tension won't be same everywhere. Okay. So we derived an expression for tension at a random distance. Then based on that, we wrote stress, elongation. Elongation in one element we calculated. Then we integrated that to get the total elongation. Something similar we did now also. Okay. Now this part, elongation of a wire under its own weight, is there in your board syllabus also. It's there in your textbook actually. So you should be very comfortable with calculating elongations even in cases of non-uniform stress. Okay. Let's try one more problem. Okay. Suppose there's a wire like this, and at one end, assume a force 3F is being applied. Then at the midpoint, see, it's a uniform wire. Area of cross section is same everywhere. Material is same everywhere. At the midpoint, let's say a force 2F is being applied. And at the left end, a force F is being applied. So the net force on this wire is 0 only. 3F to the right side, 2F and F to the left side. Net force is 0. But the forces are not applied only at the ends. Two forces are applied at the ends, but one force is applied at the midpoint. Okay, this doesn't look like midpoint. Just let me adjust it a little bit. Okay. The aim is to derive the elongation. Total length is given L. Area of cross section is A. Young's modulus is Y. If needed, you can take total mass as M, but I don't think it will depend on that. We have to derive the total elongation in this wire. Okay. Now, Basically, how you derive elongation is by using this formula. Delta L is equal to stress F by A multiplied with natural length divided by the Young's modulus. If the stress is same everywhere, you can apply this at once and tell what is the total elongation. But if the stress is not same everywhere, then you will have to split it into small parts on which the stress is same. Okay. Try this all of you. I'll give you all 3 minutes. Net force is 0. You have to find out the total elongation of the wire. Any answer, anyone? Okay. Can any of you tell me if the stress in this cylindrical wire will be uniform or non-uniform? Or tell me a way to check it. How do we confirm whether it's uniform or not? Okay, fine. Listen, all of you. To know whether the stress is same everywhere or not, you need to find out if the tension is same everywhere or not. Okay. Take a random cross section. Now consider this part of the wire. Okay. Wire or cylinder, whatever you like to call it. If you take only that part, see the net force on the entire system is zero. That means the net force on this part also will be zero. It will elongate a little bit, but finally the net force will be zero. Now, what are the forces acting on this part? Tell me. One force obviously is the force 3F that we are applying. What other forces act on that part of the wire? Rishi, no response. Aishwarya, anyone? Yeah, what other forces can act? Internal forces, intermolecular forces, that is tension. So there will be tension acting on that cross section this way. And the entire wire is in equilibrium, means that part of the wire will also be in equilibrium. Therefore, the tension there should be equal to 3F. Okay. So the tension anywhere in this part of the wire is 3F. Okay. Now there is a force being applied here, 2F in between. When you apply a force somewhere in between a wire, tension on one side of the wire will be different from tension on the other side. We had discussed this in system of particles also, if you all remember. Where did we come across that? Okay, anyway, we discussed that string passing over a pulley case, where the pulley was rough and the string does not slide over the pulley. There, what happens at every point of the string which is in contact with the pulley, frictions will be acting. And if friction acts on a rope, then tension will vary from point to point in the rope. Something similar will happen here also. Now you consider a cross section somewhere in the left part of the wire, this one. Our aim is to find out the tension here. Now to calculate tension here, you will have to again split the wire into two parts. One part that you can consider is this, the left part. Okay, one force F is acting, and here some tension will be acting. This part has to be in equilibrium, therefore the tension will be equal to F. That is one way to find out. Another way in which you can find out the tension there is by considering this part of the system, the right side part. Okay, the part which is to the right of that cross section, like this. Our aim is to derive the tension on this cross section, the green one. Let it be T. Now this whole part is in equilibrium. T and 2F are acting to the left side. 3F is acting to the right side. That way also you can tell that T is equal to F. Therefore, anywhere in this part of the wire, the tension is F. And anywhere in the other part of the wire, the tension is 3F. Okay, so one half of the wire is under one tension, the other half is under another tension. And your aim is to derive elongation. Sorry. Now the area of cross section is same throughout. If area is same, then wherever tension is same, the stress will be same. So you will have to split the wire into two parts. In this part, tension is F, natural length is L by 2. Okay, capital L by 2. We'll find out the elongation in that part first. Next, the other part of the wire. In the other part, tension is 3F, the length is L by 2. We'll find out elongation of that part separately. Add them, you'll get the total elongation. Okay? Therefore, elongation in the left half. What is the formula for elongation if stress is uniform? F by A. Okay. So here, see, don't blindly write F by A. F is the force which creates tension. Okay. Sorry, which creates stress. In this case, in this particular example, tension is what creates stress throughout. So you'll have to take T by A multiplied with natural length divided by the Young's modulus. Now tension in the left half is F divided by A. Natural length is L by 2 divided by Young's modulus. This is the elongation in the left half, FL by 2AY. Next, elongation in the right half. Right half also, the force which is causing the stress is tension. So tension by area multiplied with natural length divided by the Young's modulus. In the right half, tension is 3F. Area of cross section is A. Natural length of the right half is L by 2. Young's modulus is Y. So this becomes 3FL by 2AY. Add both the elongations, you get total elongation. 1 by 2 plus 3 by 2 becomes 4 by 2, which is 2. So the total elongation is 2FL by AY. Okay, that is how you approach problems like this. Basically, this idea has already been discussed. If forces act in between a wire, tension on one side of the force will be different from tension on the other side of the force. So here, 3F and F are acting at the ends, but 2F is acting in between. So in the part which is to the right of the point where 2F is acting, you will find one tension. In the part which is to the left of the point where 2F is acting, you will find another tension. Derive tensions, then from that you get stress, from that you get the elongation. Okay. Now consider a situation like this. Suppose there's a wire. Fixed to a rigid support. Okay, let's ignore gravity for now. Okay. Let's say its natural length is L. Cross-sectional area is A. Young's modulus is Y. Fine. Now you start applying a force on this wire at the other end. When you apply a force, what will happen? See, since it is fixed at one end, it's not free to move. Okay. So when you apply a force this way, the wall will also apply a force. Basically, some tensile stress will get generated in this and the wire will expand a little bit. And see, as the wire expands, the restoring forces will try to keep it in shape. So it may expand a little bit. By then, the restoring forces balance the external force. Okay. So what will happen? This wire will expand a little bit. So compared to its natural length, when it is not under any stress, its length was L. Compared to that, it would expand a little bit. Fine. Why did it expand? It expanded because we applied a force at one end. Now it will expand like this and it will settle. The other end, where it is fixed to the wall, is also experiencing a force F from the wall. We don't have to show it. The wall will exert anyway. Okay, and we know it. Let's say the elongation is X. So basically in place of delta L, I'm taking X. Now, why did it stop elongating? It stopped elongating Because internal restoring forces have balanced the external force. And see, it's important to visualize the situation correctly. When you apply force at both the ends, you are creating stress everywhere. So elongation happens everywhere. You may only see one end of the wire moving, but actually every point moves. Ultimately, what you see is one end moving. Okay, so stretching happens everywhere, not just at one end. Fine. So the restoring force has balanced the force that we have applied. Now, under the influence of the force that we have applied, the elongation that was produced is x, and now the wire is in equilibrium. Equilibrium is net force zero. If net force is zero, tension is same everywhere. And this is a wire of uniform area of cross section. If tension is same everywhere and area of cross section is same everywhere, means the stress is same everywhere. Okay. How much is the stress? F by A. So how much should the elongation be? FL by AY should be the elongation. That means F should be equal to AY by L multiplied with X. The force needed to get a particular elongation is this much. And this is what is interesting. The force becomes proportional to X. Greater the elongation you want to produce, greater the force you need to apply. What force are we talking about? External force. And external force will be balanced by internal force. That is when it stops elongating. Okay. Therefore, you can say that if stress is proportional to strain, okay, if stress is proportional to strain, see, I told you yesterday, it's not necessary that strain is always proportional to stress. Okay. But up to a certain extent, it will be. And under that assumption only, we are deriving everything. We are solving problems also. So as long as stress is proportional to strain, okay, technically this is called within proportionality limit. I'll tell you what this proportionality limit is. Basically, when you apply too much stress, no, the strain produced won't be proportional to stress. Proportionality will be gone. So only for small stresses, this is valid. So as long as stress is proportional to strain, that means within proportionality limit, you can say the restoring force developed in a wire is equal to AY by L multiplied with X. The restoring force is proportional to the deformation. Okay. Now see, we stretch the wire to the right side. X was to the right side. The restoring force is to the left. Means restoring force is opposite to the elongation. This is something very similar to what we observe in springs. What was the formula for spring force? Kx, where K is called spring constant, X is the elongation in the spring or compression in the spring. Fine. And spring force also, if you elongate it beyond natural length, force will be inwards. If you compress it, force will be outwards. So force is opposite to deformation. Here also the force is opposite to deformation. You try to stretch something, internal forces will be inwards. You try to compress something, internal forces will be outwards. Okay. So what we see here is that a stretched wire behaves very similar to a spring, stretched spring. Okay. The only difference is the proportionality constant. In case of spring, it's the spring constant K. In case of wire, K is replaced by AY by L. So you can say AY by L is equivalent to spring constant. So what this suggests is that a stretched wire, simply a wire, can be treated as a spring. You try to stretch it, it will elongate a little bit, but the internal forces will prevent elongation beyond a certain extent. So the force developed, the internal force developed is proportional to the elongation, just like in case of a spring. So remember, stretched wire behaves as a spring, but only within proportionality limit, only as long as the stress is proportional to strain. And what is the equivalent spring constant of a wire? It is AY by L. In place of spring constant, you can use this. Now we know that a stretched or a compressed spring stores potential energy in it. Okay. The potential energy stored in a spring. Can one of you quickly recollect and tell me the formula?
Half kicks.
Good. Just a moment. Yeah. The potential energy stored in a deformed spring is half kx square, where k is its spring constant and x is the deformation, elongation or compression. Now, the internal force developed within a wire is similar to the force exerted by a spring. So, here also you can talk about potential energy. Potential energy stored in a stretched wire. Potential energy of a or in a stretched wire. So, a stretched wire behaves similar to a stretched spring. So, if a spring can store potential energy in it, a stretched wire also can store some potential energy in it as long as it is within the proportionality limit. So, potential energy in a stretched wire, you can express it this way: half. What is the spring constant of a stretched wire? Ay by L multiplied with x square, where x is the elongation in the wire. Simple. Okay. So first we discussed how a stretched wire is similar to a spring. Then we are directly using the spring potential energy formula to tell the potential energy in a stretched wire. Now there are many ways of expressing this. Half into Ay by L into x. X is nothing but elongation. You can write it as delta L also squared. Okay. So this can be written as half. Now elongation in a wire, delta L, you know, is FL by AY. So one of the delta L terms can be replaced with FL by AY. The other delta L term is still there, multiplied with AY by L. Okay. So this becomes, now why I do this is because half F by A becomes the uniform stress in the wire. And remember this formula that we just derived. Okay. The potential energy stored in a stretched wire, half AY by L into x square. This is valid only when the stress is uniform. Okay. That is the case for which we derived this formula. What to do in case stress is non-uniform, we'll discuss later. We are using this formula, right? Elongation is equal to FL by AY. This is only when stress is uniform. Okay. So everything that follows will also be valid only when stress is uniform. So half F by A is stress. Next, this delta L and this L. Delta L by L, that is strain, elongation divided by the natural length. And what remains? Area of cross section can be cancelled. Young's modulus can be cancelled. Okay, wait, area of cross section cannot be cancelled. We have used it in stress already. So Young's modulus is the only thing which can be cancelled. So half F by A delta L by L, and you will be left with A delta L in the numerator. A into delta L. So this becomes half F by A is stress, the uniform stress. Delta L by L is the strain. A, wait. Delta L is already considered, no? L is left in the numerator. Delta L by L strain we have already taken. L is left in the numerator. A into L, area of cross section multiplied with the length, becomes the total volume of the wire. So the potential energy stored in a stretched wire can be expressed this way also: half stress strain volume. Okay. You may even be asked, what is the potential energy stored per unit volume? Then it becomes half stress strain. But only when the stress is uniform. Keep the condition in mind. Okay. So what we have just seen is how a wire can be compared to a spring. A wire under uniform stress behaves like a spring as long as it is within the proportionality limit. So what is the equivalent spring constant of a wire? Ay by L. With that, whatever formulas you have in case of spring force, spring potential energy, same formulas can be applied to wires also. Okay. Let's solve an interesting problem based on this. Let's consider this situation itself, stretching a wire. Okay, let's assume stress is uniform, the wire is uniform, proportionality limit, okay, like it is within proportionality limit and all. Listen to this carefully, all of you. This is important. Suppose there is an unstretched wire and you stretch it by applying a constant force, capital F. Now you are applying a constant force, that's fine. The material will apply a restoring force. The restoring force applied by the material will not be constant. Why will that not be constant? Because restoring force depends on how much the material is deformed. So let's consider an intermediate situation like this, where the wire is still getting elongated. Final elongation, let it be x, that's fine. But in between, okay, let's say there is a random elongation like this. This small elongation, you can call it as a, maybe small a, or any letter you can use. Then the restoring force also will be small. If the elongation is small, the restoring force is small. The applied force is large, capital F. Restoring force is not as strong as the applied force. Okay. But eventually, the restoring force will balance the applied force. That is when elongation will stop. Okay. So that final elongation, let it be x. Okay. So as the wire elongated, there were two forces acting. One force is the external force F that we are applying, the other is the restoring force. Now see, the external force we are applying and the elongation of the wire are in the same direction. Okay, in fact, the point where we are applying the force is the right end of the wire. That end is moving to the right side. So external force does positive work. Okay. Internal force, on the other hand, internal force is to the left, but particles are moving to the right side. So internal force must be doing negative work. Let us derive expressions for work done by these. And it's very easy. External force is a constant force, and the displacement of the point of application of the force is x. They are in the same direction. Therefore, work done by the external force will simply be Fx. Force, displacement, constant force, they are in the same direction. So directly you can write Fx. Next thing is work done by internal forces. Work done by internal force is behaving like spring force. Okay. Or you can say internal force is a variable force. You integrate and find out. I'll directly use the result. Negative of change in potential energy. Okay. Now, when the elongation is x, the final potential energy in the wire is half into spring constant Ay by L into x square. Therefore, the work done during this elongation should be minus half spring constant Ay by L multiplied with elongation x squared. Okay. Now we know x is equal to FL by Ay. So 1x I will replace with this. Why? Because I want to compare work done by external force and work done by internal force. External force was simply written in terms of F and X. Internal force, we got a slightly complicated expression. I'm trying to simplify it. Okay. So what we can do is substitute 1x as FL by AY. Then what happens? Minus half AY by L into 1x I'll keep as it is. The other x I'll replace with FL by AY. L by AY, L by AY cancel. You get minus Fx by 2. This is what is interesting. The force we applied did a work of Fx, but the internal force only did a work of Fx by 2. Doing work means what? Giving energy. We supplied energy Fx. Internal force removed the energy Fx by 2 because it did work minus Fx by 2 means it removed energy Fx by 2. Where is the remaining energy going? Okay, let me explain the situation once again to all of you. While stretching a wire, we stretched it by applying a constant force and we did a work of Fx. But as the wire stretches, the restoring force will be a variable force because restoring force depends on the amount of deformation. It slowly deforms, no, gradually deforms. So step by step, the deformation increases, restoring force increases. So restoring force was a variable force and it only did a work of minus Fx by 2. Okay. So we supplied an energy of Fx. Okay. Restoring forces removed how much energy? Fx by 2. Where is the remaining energy going? Think carefully, all of you. I'll give you a minute. And I want all of you to come up with some answer at least. Use your imagination. What could have happened? Think and tell. I got one answer. I just want to discuss that answer. The answer was that it gets converted to potential energy. See, the restoring forces did a negative work. No, that itself is getting, like I told you, restoring forces removed some energy. They converted it into potential energy. Okay. So work done by restoring forces, which is minus Fx by 2, gets stored as potential energy. But where is the remaining energy going? I mean, what I mean to say is we supplied an energy of Fx. Fx by 2 is getting stored as potential energy through this, through the work done by internal forces. Okay. Fine. Maybe I should not have used this term removed. So I should have used restoring forces convert Fx by 2, half of the given energy, to potential energy. Where is the remaining half going? Okay. I got only one answer. Fine. And the answer is that it gets converted to heat. Correct. Correct. Okay. You can try this also. You can actually feel this. Take a rubber band. Fine. Not now. Do it later. Take a rubber band without stretching the rubber band, or you ask someone else to hold the rubber band and place it on your hand, preferably this part. Okay. Just without stretching the rubber band, ask them to place it here. You can feel its temperature. Fine. Then you ask them to ask them to keep it in contact with your skin and suddenly stretch the rubber band. Okay, quickly you have to stretch it. Then you will be able to feel the rubber band getting heated. Okay, when you stretch the rubber band, suddenly it gets heated. Okay, you can feel the rise in temperature. Okay, so when you stretch a wire, same thing happens. When you stretch a spring, also same thing happens actually. Yeah, by applying a constant force, if you stretch a spring, only half of the work you do gets stored as internal energy, or not internal, sorry, potential energy in the spring. The other half gets lost as heat. Okay. So yeah, stretched wire under uniform stress behaves like a spring, provided it is within the proportionality limit. And you know, like we discussed how, what is it, spring constant and all. Fine. Now consider a situation like this. There is a cylinder. You all must have experienced this also. Suppose there is a, and let me not even use this. Suppose there is a thread or stick also you can consider. Suppose and you want to break the thread, snap the thread by applying forces. Okay, let's say the thread is rigidly connected at one end to some support and you want to break the thread. Now you apply a force, you start increasing the force. At one particular amount of force, the thread will snap. Okay. Next, you consider a bundle of threads. Okay, like this. Assume they are also fixed at one end to a rigid support, and on all of them together, you start applying a force. Tell me, if the force needed to snap one thread is F naught, how much force will you need to apply to snap three threads, a bundle of three threads like this? Is it the same force? Will you need a greater amount of force or a lesser amount of force? First, tell me that.
Sir, slightly greater.
You will need a greater amount of force. Okay. Like from everyday experience, we can tell that. And if the threads are exactly identical, okay, and you perform the experiment in ideal conditions, you will see that for three threads, the force needed will be three times the force you need to break one thread. Okay, it will be exactly triple. Fine. Now, why does this happen? The same reason, like the same explanation that we started discussing the chapter from. Like if you apply a force on the wall with your hand, it may not damage the wall. But if you apply the same force through a nail, it will damage the wall because the damage caused depends on force per unit area, not the exact force. Okay, not only the force. Now, here in one case, when you apply a force F naught, we see that the thread is breaking. Let's say the area of cross section of one thread is A naught. A force F naught is able to break one thread, okay, or snap one thread, means the stress for which the thread is snapping, we call it as breaking stress, is F naught by A naught. Once you generate that much stress, it breaks. Now, for three threads, we see that the force is tripled. Why? Because the area of cross section is tripled now. A naught, A naught, A naught. The effective area of cross section is 3 A naught, and you will see that you will need a force of 3 F naught to break it. So, what is the breaking stress for a bundle of three threads? 3 F naught divided by 3 A naught. It's still F naught by A naught. Okay. The amount of stress you need to create to break something depends on the material. The amount of force you need to apply depends on the dimensions of the object. Okay. So what I mean to say is, suppose there is plastic. Okay. You apply a certain force on one plastic rod, it will break. But suppose there are multiple plastic rods, okay, tied as a bundle, and you want to break that, the force you need to apply will be greater because to break something, you need to generate a certain minimum amount of stress. Stress depends on force as well as area of cross section. Okay, so materials break when you apply a certain amount of stress on them. That is called breaking stress. Sometimes that stress can easily be achieved by applying a small force because if the area of cross section is less, the force needed will also be less. It will break. If the area of cross section is more, then you'll need to apply more force to create the same amount of stress and break the object. Okay, so remember, breaking stress depends on material with which the object is made. The force that you need to apply to break should be calculated based on that. Stress and area together can tell you how much force you need to apply. Okay, but the stress is fixed depending on the material to material it can change. Okay, so suppose you apply a variable stress on a wire. Okay, let's say there is a metal wire and you start applying stress on it. Consider stress on the y-axis, strain on the x-axis. Strain is nothing but a measure of deformation. Now when you don't apply any stress, there won't be any strain. Without stress, why will the wire elongate? It won't. Okay, start increasing the stress you apply. You will see that the strain produced will increase proportional to stress up to a certain extent. Okay. As you increase the stress applied, the strain also increases, means the deformation increases. And you will also see that if you remove the stress applied, the wire will go back to its original shape. Okay. What See, this property of going back to original shape is called elasticity. Fine. So as you apply increasing stress, the strain increases proportional to stress, and you will also see that the object will come back to its original dimensions when you remove the stress. So elasticity is there, proportionality is also there. Okay. Initially, as you apply small amounts of stress, elasticity, proportionality will both be there. But you keep on increasing the stress, strain will increase, means deformation will increase. At one point, you will see that the stress strain curve will no longer be proportional. Elasticity will still be there. Okay. This is behavior, this is based on experimental evidence. Okay. This is not something we uh, can justify. It is found to happen like this. Okay. So when a wire is stretched, it so happens that up to a certain extent, stress will be proportional to strain and the wire will be elastic also. Elastic means you remove the stress, the wire will come back to its original length. But beyond a certain point, you will see that elasticity will still remain, but proportionality is gone. Means the graph won't be a straight line passing through the origin anymore. And that way, you increase the stress, strain will increase up to a certain extent. Then, at another point, the elasticity will start getting lost. Okay. So, this yellow point, let's name it as A. A is called the proportionality limit. Okay. Till then, stress and strain are proportional to each other. The graph will be a straight line passing through the origin. Beyond A, there's no proportionality, but elasticity is still there. Means you remove the stress, the wire will still come back to its original dimensions. But that won't happen for too long. You go on increasing the stress. At one point B, the wire will start losing elasticity. So B is called the elastic limit. What happens beyond elastic limit? See, the wire is losing elasticity means what? Restoring forces have become weak. Okay. If restoring forces become weak, you can easily stretch the wire. Fine. So what will happen beyond B, beyond elastic limit, even for a small amount of increase in stress, you will get a lot of strain like this. Okay. See, the stress increased only a little bit, but look at how much strain you were able to produce. Fine. Because internal forces or restoring forces have become weak. The object is losing its ability to come back to its original shape. Okay. So this property is called yielding. Okay. The material starts to yield, means it is giving up. Right. But some elasticity will still be there. So in this region where the material is yielding, if you remove the applied stress, the object won't go back to its original shape, but little bit of restoration will take place. Okay. Up to B, there will be complete restoration. Beyond B, there will only be partial restoration. And that restoring ability will decrease gradually. Okay. Then at one point, it will totally lose that restoring ability. Okay. That point is called elastic fatigue. So after that, it won't be able to restore at all. Okay. I mean, you remove the stress applied, the wire won't come back to its shape, original shape at all, not even a little bit. Okay. And you continue applying the stress. See, there's no restoring force, no. Beyond C, there's no restoring force at all. You can easily produce strain. So you don't even have to change the stress much. Just increase it a little bit. Okay, sometimes you can decrease also, not necessary. It has lost its ability to regain the original shape. Then what will happen? Eventually, it will break. So the final point on this graph is the breaking point or the breaking stress. Or sometimes they also call it as fracture point. So this is the behavior of a wire, okay, behavior of a stretched wire under increasing stress. Okay, this is based on experimental evidence, as I said. Okay. So when there's no stress, there won't be any strain. Therefore, the graph starts from the origin. As you increase the stress applied, strain will also increase. Up to a certain extent, they'll increase proportional to each other. So you can also say that the slope of the graph here, O to A, okay? Effectively, slope is what? Delta y by delta x, y coordinate by x coordinate, stress by strain in this case. And stress by strain is nothing but Young's modulus. So O to A, the slope of the graph is the Young's modulus itself. They can ask you questions based on this also. For different materials, they'll give you graphs like this and ask you which material has higher Young's modulus, which has lower Young's modulus, what is the ratio of Young's modulus. Such questions can be asked. So as you increase the stress up to a certain level, stress will be proportional to strain. So proportionality is there. Elasticity will also be there. As you continue increasing the stress, first the material will lose proportionality. Okay, means stress will stop being proportional to strain. But elasticity will still be there. Means if you remove the external stress, the material, the wire will still come back to its original shape completely. But if you go on increasing the stress beyond a certain extent, beyond the point B, it will start losing its ability to come back to its original shape. It will become partially elastic or partially inelastic, you can say. Okay. There, once it starts losing its ability to come back to original shape, it will become very easy to produce elongation. Okay. So that process is called yielding. For a small change in stress also, you'll get a lot of strain. So it loses its ability to restore, loses. At one point, it is completely gone. That is point C, which is called as elastic fatigue. Means the material is now exhausted. It has no more ability to come back to its original shape, even a little bit. And then free expansion will take place and ultimately the wire will break. Yeah. So finally, fracture point or breaking point. Okay. So we'll stop it here for today. So basically what we discussed today is how to find out elongation in case of non-uniform stress. Okay, we solved a few problems based on that. Then we compared a stretched wire to a spring. Remember the conditions. The stress has to be uniform and it has to be within proportionality limit. Means stress should be proportional to strain. Only then a stretched wire can be compared to a spring. And we wrote the expression for potential energy stored in a stretched wire, which can also be expressed as half stress strain volume. Then we discuss this case. Whenever you stretch an object, some heat will definitely be produced. In some cases, you will be able to feel this also. Later, you all try that, try what I suggested. Ask someone to place a rubber band on your skin, okay, where it is very sensitive. Place it without stretching, you will get a feel of its temperature. Then ask them to stretch it suddenly while keeping it in contact with your skin. Then you will be able to feel the change in temperature. Okay, heat will get generated. Okay. Then we talked about breaking stress. This is very important. Breaking stress, the stress needed to break something depends on the material. Fine. The force that you need to apply to break something depends on material as well as the dimensions of the material. Okay. Because to generate that kind of stress, in some cases you will need little bit of force. In some cases you will need a lot of force. Okay. So depending on the dimensions, the area of cross section, you will have to apply the required amount of force to break the object. And then we talked about behavior of a stretched wire under increasing stress. Fine. There are two other, like last class and this class, all we discussed was about longitudinal stress, longitudinal strain mostly. There are two other kinds of stress, tangential stress and volumetric stress. So next class, we'll discuss those two and finish this chapter. This is a small chapter only. And next class, I'll take on Wednesday, usually only. But I like from this week, we will have to do at least 4 classes a week because we have to speed up. Wednesday's class will finish solids. Just a moment.